Welcome to my first lab about charged tapes. We're going to need to remember some key concepts. First, gravitation, gravity near Earth's surface, which is 9.8 meters per second squared. We're going to be working there. You need to get there by these variables. We're also going to remember Newton's second law, that the acceleration is proportional to the net force. And that's going to be important in showing that the tape is not moving because the net forces are zero. Some other key concepts are the electric force, which is similar to gravity force. This right here does not take into account the vector, but by calculating the electric field vector, which is a sum of all the electric fields in the area, as you can see here, you can get a vector force on any object. And then we're going to need these standard variables. So K, which is seen here, 4 pi coulomb, whatever, 8.987 times 10 to the 9th newtons meters per second coulomb squared. This is Coulomb's constant. And then we're also going to need the standard charge of a proton, which is 1.602 e to the negative 19th coulombs. So the purpose of this experiment is to show that two pieces of tape repelling each other are going to essentially oppose the effect of gravity, suspend themselves, and then we're going to use that through a computational model and also a qualitative analysis and determine the excess charge on the tape. So some key assumptions is that the tape is a point charge. That way we can simulate it pretty easily, that they have equal charge, and that they are only moving in the y-axis, and that the net force is zero. So the procedure, first you're going to tape one tape to a table, and then you're going to put another one, this U-tape on top. You're going to rip it off. It's going to be charged. You're going to do that again. You're going to put them near each other, and then you're going to put them near a plastic pen that you can rub on some fabric or rub through your hair. And that's going to kind of help you determine the sign of the charge, because the pen is going to be negatively charged. Then you're going to suspend one of the tapes between two towers, raise the other beneath it, and notice the distance between the two in the y-axis. So as you can see here, the net force is going to be zero between the electric forces and the forces of gravity, which are going to be equal and opposite to each other. So we're going to observe it. The distance that we observed in the lab was 1.5 centimeters. We also measured the tape's dimensions, its length, its width, its surface area, and then approximated its mass. This is super important for later calculations. The atom area is going to be that tiny, tiny little approximation here. It's taking into account all of the different atoms inside of the tape and averaging them. And then what you can do is you can take these numbers here and you can calculate the approximate number of atoms in the tape. You also are going to notice that the tape repel each other, so they have the same charge, and that because they're attracted to the negatively charged pen, they must be positively charged. What you can see here is you can see the force of gravity by calculating the tape's mass. Then you can show that that's opposite to the electric force. And then what we can do is we can use that, we can reverse the equation to find the approximate charge, which is 7 e to the negative 9th coulombs. The electron deficiency, which is going to be that charge times the number of electrons, is going to be this approximate number of electrons that you would need to get this total charge here. And then you're going to find the ratio of this number of electrons to this number of atoms total, which is about 1 to 9.13 e to the 6th. So very few of them are a deficit of an electron. We're also going to show this through a computational model, which you can see here, the little calculations. We need to put in K, we need to put in G, we need to find the distance, the gravity, the electric force, and then we can find Q from that. We're also going to find the ratio by the same methods that were just described. And you can see here all of the code. You can run it. You see there's the electric force, there's the force of gravity, here's that suspended tape represented by a point, and here's that tape that we're pushing out. And then it's going to tell us the gravitational force, the electric force, the magnitude of charge, the number of electrons, the deficiency, etc. And then what we're going to do is we're going to take that and we're going to show that this Q is pretty much the same, 7.01. The tape is positively charged, which we already determined, and we modeled this assuming that the net force was zero. Some errors that we could have made were the measurement of the height and relative distances, and also just that the U-tape were not perfectly aligned, and just some broad estimates, rounding errors, etc. So what if the electrons had positive charge? Would it be different if everything was swapped? No, nothing would really change. The only thing that matters is the difference in signs, the fact that they're opposite, not really that one of them is inherently positive or inherently negative. If it was negatively charged, the tape, it would have just been repelled by the pen. And why is it so important not to handle it? Because when you handle it, the electrons transfer between the surfaces. That can weaken the charge magnitude, and then that weaker magnitude would make the distance change and not be representative of the problem. Thank you.